Okay, so now we're going to look at some of the assumptions of regression. This is the material on page 299. So let's go to data, data analysis, regression. We have our data set from the last video, i.e. market value is Y, square feet is X. We're going to stick with pretty much everything, but this time we're going to have a look, and we're going to look at some residual analysis. We're going to click residuals, standardized residuals, residual plots, line fit plots. I'll also show you the normal probability plot, but I don't think it's a huge amount of use in this context. Okay, so we have the regression as before. I'm going to show you each of these plots in turn. The first thing we'll look at is the residual plot. So let's just get this a little bit bigger. And let's format this axis a little bit. And bounds. Okay, that's a kind of a little bit better. And these are the residuals. Now, we need a few things when it comes to residuals, and I'll just take a snippet and I'll talk about each of these in turn. Let's just get a little bit more, move up here so we have a little bit more kind of blank room. We won't remove that for the moment. Okay, so let's just kind of, let me do a snip. And let me move back to red. So the first thing we're interested in is linearity. And this is going back to, when we talked about the correlations. So let's just draw a little plot with X and Y. If we had this sort of pattern, and then we try and fit a regression line, then that is not linear. That is not linear. In fact, you would get kind of residual graph that looked a little bit like, so these residuals here, these are basically, each residual is going to be it's just going to be Y minus Y hat, i.e. we sometimes call this the error or epsilon. You'll sometimes see this called. And if you look at that, Y minus Y hat here, if this is the predicted line, let's just look at our errors. So Y minus Y hat starts out negative, and then it kind of goes positive, and then it goes negative. So this would be the residual plot for this example. So you could see in this instance, this would not be, this would not be linear. I.e. again, not linear. And in fact, let me just go back to where I did a scatter plot for this. You see here, this looks relatively linear. There's a few little outliers here, but on the whole, this looks relatively like a linear relationship. So we don't have to worry too much about that. Okay, so the next little thing we want to discuss is heteroskedasticity. And in fact, what I will do is I will do another snip. So this is the next assumption. Again, these are page 299 to 300. And I'm actually, I'm skipping out the normality of errors for the moment. I'm going to go back to that in a minute. So this is going to be normality of error. Sorry, this is going to be homoskedasticity versus heteroskedasticity. Okay, and I'm not just writing long words for my health. So I'll show a few examples. If something's homoskedastic, so we have the X and then the residuals, then you would generally get the same magnitude of errors throughout the graph. So we don't get much more error as X increases. That is homoskedastic. So I'll just say homo. And let's just have another example, which I'll call hetero. And these are the residuals. Again, how big our error is. And if your errors start off very small, but then they get bigger and bigger and bigger, then that's heteroskedastic. And generally, that's considered a bad thing. So we want homoskedasticity. Maybe I should have used blue and then red the other way around. So we want this, and we don't want this. One way of transforming heteroskedasticity into homo. So say we have heteroskedasticity. And generally in an application such as this, where we're dealing with something like prices, then we are liable to get heteroskedasticity. If we estimate the price, say of a $50,000 house, maybe we're plus or minus $5,000 in our error. If we estimate the price of a, say, $5 million house, we might be plus or minus, 100,000. Now, a little bit beyond the scope of the book, but one way of kind of solving heteroskedasticity would be, rather than plotting y against x, if we have a variable that lends itself to heteroskedasticity, like, for example, the price of a house, is that we actually take the log of the values rather than the values. And there's all different kind of ways of doing this. We could take a simple log. There's something called a Box-Cox transform. But these are kind of really, I would definitely, if you see this kind of pattern of residuals a little bit like this, you can play around with like a log transform of your data. But again, something more advanced is a little bit beyond the scope of the course. But again, just feel free to, pop on the discussions, and I'd be happy to chat about that in more detail. Okay, let's get rid of that. So the next thing we want to look at is the independence of errors. And we'll actually do the normality last. So let's just take another snip. So we want the independence of errors. And the idea is that, you shouldn't be able to see, there shouldn't be a relationship here. So you shouldn't be able to, and these are relative independent, you shouldn't be able to almost guess one error from the previous error. They should almost be, the errors should be random. So this we would say is relatively independent. Now, if they're not independent, they could be autocorrelated. And this is basically just saying that, if something's autocorrelated, then there's a correlation between a certain value. So let's just say this was our error. We'll use R for correlation. There's a correlation between our error at kind of time t and our error at t minus 1. And this would look like something like, you know, you would have high errors together, and then maybe you would have low errors together. So if something was autocorrelated, it would maybe look a little bit like this, in that the error is kind of almost similar to the previous error. So that would be autocorrelated. That would be positive autocorrelated. And the opposite would be maybe negative autocorrelated, which is very rare. And in this instance, say we have, so that would be X, and that would be residual. X and residual. You would have like a high followed, but then it goes opposite, high, low, something like this would be negative autocorrelated, which you're not going to get in practice. Now the book defines, but wonderfully doesn't actually, we don't have this in the Excel data analysis tool pack, the kind of Durbin-Watson coefficient. And this is just the difference in residuals. So again, we're calling it E. I'm just going to call it epsilon for error. And we're calling the time periods I rather than T. Let's just stick with my notation. So we call T equals 2 to the number of time periods. And basically, look, if you see that, if the errors are close to each other, so in this instance, this value would be small. But if there's a huge difference between the errors that are next to each other, then these values on the numerator would be large. You'd have this big difference between the residuals, and generally there's this rule of thumb, you know, below 1 is autocorrelation. And above 2.5 is negative autocorrelation. Now you could probably work this one out. You could probably calculate this yourself, but again, it's a little bit beyond the scope of the course. So the last thing we're looking at is the normality of the errors and whether the errors look like a normal distribution. And there's a few different ways we could do that. I'm going to kind of start with this. I'm going to move this thing out of the way for the moment. Okay, so here we have the actual residuals. Now, there's a few different things we can do with this. The first thing I want to do is I want to like plot these residuals. I want to do it using a histogram. So let's actually copy these. Let's just make them, yeah, let's just put them down here. Let's put them out of the way. And what I want to do is I want to create the histogram, and I want to do it on bins based on the standard deviation. So I'm going to call me my bins, and go to -4, -3, -2, -1, 0, 1, 2, 3, 4. And we've got this crazy one at the bottom that's greater than 4. And this is going to be 5. And what this is doing is you see we have the residuals, the errors, and then we're basically standardizing them, like subtracting the mean and divide by the standard deviation. And what we're going to do is we're just going to plot a histogram of these standard errors. So I've got my bins here, so data analysis, histogram. My input range is my standard residuals. And the bin range in here. And we're just going to stick it possibly here. Okay, so let's not forget that we're actually including labels and chart output. I think that's pretty much it. Okay, and here we go. And you see this histogram. It looks a little bit like a normal distribution. We've got a high peak in the middle, and then we have tails. This is never going to be normal, completely normal, particularly if we have a small amount of data. If we had like 1,000 houses, then you might be able to see more clearly whether something was normal or not. There's actually statistical tests you can use to test normality. There's one called the Kolmogorov-Smirnov, which can be used to actually check the normality of things like residuals. But we'll just show a graph and say, hey, that looks pretty much normal. The other way you can look at kind of whether something's normal or not, you can actually use a normal probability plot. This isn't a huge amount of use. Generally, we would look at we'd have a kind of a line here, and we would actually see which would be the line that if the data were normal, and we'd see whether how far we actually go off this line, so how far we are from straight, and we can see we deviate from normal a little bit towards the edge, but it's very hard to check normality with this type of plot. And usually there should actually be a line which is the line of normal, so we won't worry about this too much. We'll just focus on the histogram. The last thing we want to do, which is why I moved the residuals over here, I want to play around with these again, is we may want to look for outliers in the data. So again, let's go back to our original version here. This one looks a little bit like an outlier, and sometimes outliers can really skew your regression. So either you may say, hey, you know, this observation is so far out, it's hurting my model, or let's just have a look at this again. It could be that this house was in like incredibly good condition, which maybe tells us that there's some unobserved, there's something in our data that we're not including in our model that we should actually include in our model to make it a better model. But for the moment, let's just say, hey, if we have something that's maybe more than 3 standard deviations away from the a residual that has more standard residual that's more than 3 standard deviations, then that's possibly going to be an outlier. And let's just kind of have a look at this. So we could set like absolute value. So we're looking negative or positive here. So we'll just call ABS, the standard residuals. We're going to go all the way down here. And we could actually maybe do some formatting on this standard value. So let's select these values. And let's just do conditional formatting. Let's do some icon sets. And let's do some traffic light shapes. Now let's just manage rules. We've got an icon set, so let's edit it. And let's just say it's green when we are, we'll say it's red when the value is greater or equal to 3, orange when it's greater or equal to 2. We'll say number. So red greater than 3, orange greater than 2. Otherwise, it's going to be green. So we're basically just flagging large values. And we see here, We have one slightly suspicious observation with a residual of which is 2 standard deviations over 2. And then we have this really large outlier, which is basically our last point, the 42nd point in the data set, which is this one here. So again, it's this house here that has moderate size, but it's $120,000, which is this one, which is the one, just by looking at the graph, we could have seen that was an outlier. Okay, so just to kind of go over what we did some analysis of some of the assumptions of regression, and we did lots of plots. We looked at linearity, we looked at homoscedasticity, we looked at independence of errors, and then finally we looked at normality of errors, and then we checked if any of our observations were outliers. And we found that this last observation, this one here, was quite a strong outlier, but again, we could have probably seen this one from an actual scatter plot.